Okay, so any other questions besides the homework? There were some problems with the homework. I will update it hopefully today. So just check the homework tomorrow morning. So there will be some corrections. The new homework will come on Friday. Now it will be the same homework, but there were just a couple of typos and some parts of the questions that didn't make sense, etc. No, you are doing that. I mean, I will just change a few parts. But I would have expected you to have already finished it. Okay, any questions before we start? Now, up to now, what we had done was we basically had seen that the electric field of a general charge distribution, we could write it in this form. Given any volume charge density, this was the form of the electric field. And although in general we don't know all of the charge density everywhere in the universe, still just the fact that it is possible to write the electric field in this form for the unknown charge distribution allowed us to determine certain properties of this electric field. Like we had seen that the divergence of the electric field was equal to rho over epsilon 0, and the curl of the electric field was equal to 0. Well, in integral form, I mean, the divergence theorem, the divergence of the electric field is nothing but the familiar Gauss law. E dot ds, the integral of the electric field over any closed surface, this was equal to the charge inside divided by epsilon 0. And one point to keep in mind when you are especially using this expression of the Gauss law is here E is the electric field created by all the charges, both the charges inside our closed surface and also outside our surface. Whereas the right-hand side depends only on the charges inside our surface. This is the total electric field, but this is only the charges inside my surface. And the curl of E equal to 0, it told us that the integral of the electric field over any closed loop, this was equal to 0. You just imagine any loop that you like, and then if you integrate the electric field around that loop, that closed loop, you should get to 0. So this was basically what we had done in the previous 2 weeks. Any questions on these? Any questions on the application of the Gauss law, the curl, etc.? Now we will pick the curl is equal to 0 or the integral form of E dot dl. So, and follow the consequences of this law. So what does this law imply? That either this one or that the curl of the electric field is 0. So this law just tells me that just take any loop that you can imagine. Let's imagine a loop that passes through an arbitrary 2 points, A and B. Now the integral of the electric field around this loop is nothing but the integral from A to B of E dot dl plus the integral from B to A of E dot dl. Remember, the integral is just the summation of many terms, each one of which is very small, infinitely many of them. So I'm just dividing those terms in the sum into 2 parts. I mean, those terms are obtained by just dividing our path into very, very small segments, calculating the electric field on each one of those segments, multiplying it with this vector that is along that segment and that has the length of that segment. And you calculate this one for each one of the segments and sum them all up. So I'm just dividing it into 2 parts. In one, I'm just summing the contributions from the segments along this path, and in the other one, I'm just summing the contributions along the other path. Now, if instead of going from A to B, let's say in this one, or let me write it in this form, this is the segment 1, this is the segment 2. Segment 1, segment 2. Now, instead of going from A to B, if we go from B to A, in each segment, the only change is that the DL changes sign. Well, if a vector changes sign, it just means there's a minus sign. It acquires a minus sign. So the same, these two terms, I can write it as from A to B of E dot DL across 1 minus from A to B across 2 of E dot DL. And this should be equal to 0. Well, this basically tells me that if I take the integral of E dot DL over path 1, connecting the point A to point B, this is the same thing as going from A to B across path 2 of E dot DL. So I have these two different paths from A to B. Well, since the loop was an arbitrary loop passing through those 2 points, these 2 paths are arbitrary paths. You can just change them whichever way you like. The conclusion still remains the same. And no matter how you change them, the integral of E dot DL does not change. So in general, a path integral will depend on how you go from point A to point B. But for this special kind of vector field, now the speciality of this vector field is that the curl of this vector field is 0. So if you have any vector field whose curl is 0, in that case, this integral along a path connecting two endpoints does not change as you change your path. So it only depends on point A and point B, where you start and where you end. It doesn't depend on anything else. So essentially, we can talk about this function now from A to B. And this will be a function of the point A and point B only. So this will be crucial for us. So we have this line integral over a line connecting A to B. In general, this line integral depends on what kind of a path you take from A to B. But for the electric field, since its curl is 0, this integral depends only on A and only on B. It doesn't depend on the path. So this function over here, the value of this function depends only on these 2 points and doesn't depend on how we go from point A to point B. So we don't have to specify a particular path to evaluate this function. Now we will give it a name. Let's call it V at the point A. This will be equal to minus from O to A of E dot DL. Well, why do we have that minus over there? Now, that we will discuss on Friday. I mean, when we talk about, well, the basic idea of having this minus sign over here is just think in terms of the work done as you are carrying a charge. On Friday, we will be discussing about the energy. Now, if you the work done will be the proportional to integral of the force acting on it. The force acting on a charge is Q times the electric field. So if you multiply this thing by the charge, by a test charge that you put in this electric field, it will feel a force, and that force will be Q times this E. So if you want to move it from point A to point B, you have to exert the opposite force. And the opposite force is minus Q times E. So that's why we have the minus. So if you multiply this by Q, you obtain the work that you should do to move the charge from point O to point A. Now, we will discuss it in more detail on Friday when we talk about the energy and the work done by the electric field. For the time being, this is how we define the potential. Well, in general, for an arbitrary vector field, if the if here you put an arbitrary vector field, there is no such function. Because given a function should depend on its arguments. In this case, the point at which you are evaluating it. But for an arbitrary vector field over here, this integral depends on how you go from this point O to the point A. It doesn't depend only on the point A. Now, this point O is just a reference point. So since this integral is independent of how you go from that reference point to the point A, then you can talk about the function of A. And as you change this point O will be fixed. You fix it once for your problem. It's just like choosing a coordinate origin. You just choose it once in your problem and it stays there. Similarly, for your potential, you choose your reference point for the potential. And once you choose it, it stays there. You don't change it. And then you look at the value of the potential at arbitrary point A. And you can just see how it changes as you change A. So this is how we define the potential. Now, of course, you can change this point O. So then what? So let's see. Let us define another potential by just changing your reference point to another point O prime. Again, this integral is independent of how you go from O prime to A. You can just choose any path. But let me choose a path that passes through O. Its value doesn't change. So I can replace this by an integral from O prime to O. And then from O to A. Now, if you look at the first term, O is a reference point. It's fixed. O prime is another reference point. It is fixed. Well, given a charge distribution, you have the electric field is fixed. So that integral is just a constant. As you change your point A, the value of this integral does not change. So that's just a constant. Some constant minus from O. Well, the other integral is nothing but our previous potential with the reference point O. So just changing your reference point only means that you are adding some constant or subtracting some constant from your potential. And we will see that just changing this thing doesn't really have any effect at all. Because basically we can only measure the potential differences. Now let's look at the potential difference between the potential at the point A and the potential at the point B. This will be equal to minus from our reference point to A of E dot dl minus from our reference point to B of E dot dl. Now plus. Now let me write it in this way. This is VA, and this is VB. But this is equal to minus from O to A of E dot dl plus from B to O of E dot dl. Well, here we have a path from B to our reference point and from our reference point to the point A. So if we just sum these up, we just obtain the integral along a path that goes from B to A that passes through O. But we know that the integral is independent of the path. So the fact that the path passes through O when we combine these two integrals doesn't really have any influence. We can just change it to an arbitrary path. The value of the integral does not change. So this is equal to minus from B to A of E dot dl. But at the same time, we know the gradients. Well, this is VA minus VB is nothing but the differential of v going from b to a. But the differential of p is nothing but the gradient of v dot dl from b to a. Okay, one thing to note, when you look at the potential differences, this is the potential difference, and there's no reference to our reference point, so our reference point just disappears. Just shifting the reference point added some constant to our potential, but when we looked at the difference, that constant just disappears, not important. Another thing, well, we have the integral of the gradient of V is equal to the integral of the electric field with a minus sign. Over any path, this point B and point A was arbitrary. We didn't choose some points that are special. We didn't choose special points. So they are arbitrary points, B and A. So if two line integrals are equal for arbitrary paths and arbitrary endpoints, then what we are integrating should be equal. But that basically tells me that gradient of V is equal to minus the E, or E is equal to minus the gradient of V. Well, in fact, this is actually the solution of one of the differential equations we have. Remember where we started with? That the curl of E was equal to 0. Okay, curl of E is equal to 0. We started from this law. And then we said that we could define some function V, and in terms of that function V, we can write the electric field in this form. But we already know that the curl of E, well, assuming we don't know what V is for the time being, if we know E, we can evaluate V, but let's say we don't know E. But if we know that the electric field can always be written in this form as the gradient of some scalar function, if we write the electric field as the gradient of the scalar function, curl of E, which is equal to the minus the curl of the gradient of V, but curl of a gradient is always 0. So if you want to solve the equation that curl of a vector field is equal to 0, the most general solution of this equation is that the vector field should be the gradient of some scalar function. Which function? Well, we don't know. For any function, V, it's the solution of the differential equation curl of E is equal to 0, or whatever V is. We should have other constraints on V to be able to determine what V is. Now, written in this form, okay, we had said that V, the potential, we can define up to a constant, because this reference point that we chose was arbitrary. We could shift it around, but shifting it around basically just adds a constant to V. But if you add a constant V, you take the derivative of that constant, that is 0. So for the same electric field, you have in fact infinitely many potentials, and they only differ by a constant. At least in electrostatics, the only difference between two potentials giving the same electric field is just a constant. Any questions? This is the definition of the gradient. This is how we define the gradient operator, gradient of a scalar function. Okay, what did we learn about the electric field up to this point in the last 2 weeks? What do you remember about the electric field? Nothing? You should be remembering something. Okay, the Dirac delta. What about the Dirac delta? Okay, so the electric field of a point charge. What's the electric field of a point charge? Which is? Rho for a point charge, what's rho? Q. This is already integrated. Okay, this is the electric field of a point charge. So what is the corresponding potential? Let us just, R prime is the position of my point charge, R is the position at which I am evaluating the electric field. Just for simplicity, let's move our origin to R prime. Nothing should change if we just move our origin. It's our choice. So let's just set R prime is equal to 0. So the electric field of a point charge was Q over 4 pi epsilon 0, R over R cubed. Now the potential of a point charge, let's say, which is located at the point R, we had defined this to be minus the integral of the electric field that dl. Well, the electric field is in the radial direction. dl, just imagine any path. dl, you can always write it in the form that is some change in the radial direction plus change in the theta, etc. I don't need the other components of this dl because E dot dl is just the radial component of the electric field multiplied by dr. This is the scalar product. The other components of dl, the one in the theta hat and the phi hat direction, they don't contribute because the electric field does not have such components. We will choose some reference point R, we need to evaluate this integral up to the point R. So VR is equal to minus reference point O up to R. ER is 1 over 4 pi epsilon 0 Q over R squared dr. Now it's just a one-dimensional integral. You can just choose it to be, do this integral, it is plus 1 over 4 pi epsilon 0 Q over, let me put the R prime over here just to differentiate it. This is my integration variable over here, this R prime. This R is the point at which I'm trying to evaluate the potential. Q over R prime starts from, let's say, the distance of my reference point from my charge, from the origin where there is the charge, up to R. So this is equal to 1 over 4 pi epsilon 0 Q over R minus Q over the distance of the reference point. Well, you can just leave it like this. This is correct. R of the reference point being some arbitrary constant. Or you can just take the limit that your reference point is at infinity. Well, we can take that limit. It is still well defined. So the potential of a charge Q, of a single point charge, just becomes Q over 4 pi epsilon 0, 1 over R. So this is the electric potential created by a point charge located at the origin. Or if it is not at the origin, this is the general form. So because here we evaluated this assuming that our point charge was at the origin, so this R is nothing but the distance of the point at which we are evaluating the potential from the charge creating that potential. So if the charge is not at the origin, so this will be the distance between the observation point and the position of the charge.
Could you repeat the part that how do you define the R values, the observation point?
You can leave your answer like that. Okay? So the reference point is arbitrary. You can choose it whichever way you like. A simple choice, which you can do in most of the cases, is when you choose your reference point at infinity. Now, you are allowed to do that because the reference point is arbitrary. You can just choose it wherever you like. You can choose it at origin, right at this point over here, or at infinity. It's up to you. It's your choice. If you set your reference point to infinity, that just means the distance from the origin is infinite. So I can just set it to infinite. If I set it to infinite, then the potential at the point R just turns out to have this form.
If RO goes to infinity, so the second term should be 0.
True.
So why isn't only R in the denominator? I mean, 1 over R, 2 over 4 pi epsilon 0, 1 over R.
Well, okay, so let me rewrite it in a different form. This is 1 over R. Now, what is R?
R is magnitude of R and R there.
Okay, so in physical terms, I mean, eventually we will be dealing with physical objects. The position of your origin, who cares about that? You can just choose it wherever you like. So without using the origin of your coordinate axis, what can you say about R?
R is the difference between origin and the point that we...
You don't use the word origin. Origin is arbitrary. If you don't use the word origin, how do you define the point R? Yeah, you see, what we did was, this is the general form of the electric field. So we just changed there's a charge on the point R prime. So we said, okay, let's not keep writing this expression all the time. Let's change it. So we have the freedom to shift our origin. Let's shift our origin to the position of my charge. So origin, in physical terms, at least in this derivation, in the physical interpretation of the origin is the position of my charge. So you are right, R is the magnitude of the observation point from the origin, but origin is the position of my charge. So R is actually, in physical terms, R is the distance of my observation point from the charge creating that potential. Now, if my charge is not at the origin, but let's say at some position R prime, at some other point, then still the physical interpretation of the potential should not change. Because, as I said, the position of origin is completely arbitrary. Your physical interpretations should be independent of your origin. So this is q over 4 pi epsilon 0 is constant. Now the r over there, as we said, that is in physical terms, the physical interpretation of this one is that it is the distance of your observation point from the position of the charge. Well, your charge is at the point r prime, your observation point is at the point r, so r minus r prime magnitude is the distance of your observation point from the position of your charge. So this r prime actually has nothing to do with this RO.
Did you choose RO as our reference point?
Yes?
But our prime isn't
You see, okay, there are a couple of things that are getting confused. One is the origin of our coordinate axis. We are free to choose it wherever you like. Your coordinate axis, you are free to choose as you wish. The other one is the reference point that you use to define the electric potential. That is RO. Now, I use my freedom to choose the origin of my coordinate axis. I have my freedom to choose wherever I like. I put it on the position of my charge. That is R prime. R prime is equal to 0. So without losing any generality, here I just set R prime equal to 0 by using my freedom to choose the coordinate or the reference point of my coordinate axis. Now there is a reference point for the potential, definition of the potential. That is the point RO. This reference point of the definition of the potential has nothing to do with the origin of my coordinates. I can choose that reference point, again, wherever I want. And eventually, I set it to be a point at infinity. Which point at infinity? Well, it doesn't matter. It can be a point at infinity in this direction or a point at infinity in that direction. I don't really care. Other questions? So you remember the electric field of a point charge, and then correspondingly there is the electric potential of a point charge. Okay, what else do you remember about the electric field? What other properties does the electric field have? Well, we already used that because the electric field is, well, what does it mean to be a field? To be conservative is that its integral over from the point A to point B is independent of the path, or that its integral over a loop is 0. So we had already used that. What else do you remember about the electric field? Okay, so let's look at that. We know that the divergence of the electric field is equal to rho over epsilon 0. Well, now we had seen that the electric field, we can write it as the gradient of the potential. But the divergence of the gradient we defined as the Laplacian. Laplacian of V is equal to minus rho over epsilon 0. So we had already discussed that if you write the electric field as the gradient of the potential, which we said that we can always do, if we do that, we already solve one of the differential equations that the electric field satisfies, that its curl should be 0. Well, there is still another equation that the electric field should satisfy. This is another differential equation for the electric field, and this translates into this property of the potential. The Laplacian acting on the potential should be equal to minus the charge density over epsilon 0 at every point. And this is what's called the Poisson's equation. Well, throughout the semester, we will be solving the Poisson's equation in one form or in another form. Now, of course, if you are looking at the Poisson's equation in a region of space that doesn't have any electric charge, so that is if rho is equal to 0 in a given region, then the Laplacian acting on V, this is equal to 0. This is what is called the Laplace equation. Okay, in classical mechanics, well, probably soon you will be doing variational calculus. Not yet. Okay, so when you do it, you will just remember this. Well, the variational calculus, I mean, you already have studied in calculus that given a function, how do you calculate its maximum or minimum? Take the derivative. Well, if you have a function of a function, then that's what we call a functional. So you give me a function, I evaluate a number from that. For example, the potential difference between 2 points, that's a number. So if you tell me some electric field, which is a function, I can calculate the potential difference. Well, that potential difference will depend on the electric field that you provide me. Now the question is, what is the maximum of this potential difference, given the electric field or given some other property? So that is what's called the calculus of variation. You will study it in classical mechanics. Now when you do that, and probably you will not be asked to do it as a homework, but just try to find, let's say you have a closed loop and you stretch some elastic film over the loop. What is the surface that has the minimum area? Just take a balloon, for example, take a ring, wrap it around the ring. Well, the shape of this the surface will be such that since the balloon tries to shrink, it will try to minimize this area. Then you can ask the question, what is the equation that describes this area of this elastic sheet? No, that function satisfies the Laplace's equation, at least approximately. If there are no, if you don't bend it very much, it will approximately satisfy the Laplace's equation.
Is there a surface that satisfies
Poisson's equation? Sure. Just take this stretch film and take a needle and push with the needle at some point. That is your Dirac delta disturbance. Rho will be there will be a Dirac delta corresponding to that needle. You are exerting a force at a single point. Or if you just press your hands, you are exerting some force, additional force, and that force can be described by putting some term over here. Now, the reason why I'm telling you that this is the equation satisfied by this stretch film with the boundary condition is that especially next week we will study that it has unique solutions. And furthermore, the solutions of this equation, the Laplace equation, they do not have a local maxima or a local minima. Just imagine that you stretch a film, well, there won't be any spikes left, it will be smooth. There won't be any bumps, there won't be any hills, except of course you are poking it.
So there is no unique solution for poison? Okay,
we will see, there's a unique solution. As long as you satisfy you are given a boundary condition. We will see that. Okay, let's go back to our electric field and the potential. What else do you remember about the electric field? For every property of the electric field that we have discussed, there will be a corresponding property of the potential. So what else do you remember about the electric field? Okay, we will do some examples in the next hour. So before going to that, up to this point, we had only discussed a single point charge. What about many point charges? How did we calculate the electric field corresponding to many point charges? There is a superposition principle. So what we had, well, we had these many point charges. The total electric, let's say Qi at the point Ri, the electric field at the point R was equal to the sum of the electric field created by the charge Qi at the position R. Well, the potential at the point R is defined as minus some reference point up to the point R of E dot dl. But this is equal to minus the sum over all the charges of the integral from the reference point up to the point R of EI dot dl. Well, that integral over there is nothing but the potential created by the charge at the point Qi. So if you have many point charges, then just calculate the potential created by each one of them at your point and sum them up to calculate the total potential. Well, if you have a continuum of charges, then this will be equal to dV, d cubed r, 1 over 4 pi epsilon 0, q over r minus r prime. Compare it with the electric field, d cubed r, well, there is the not the q, the rho. D cubed r prime, 1 over 4 pi epsilon 0, rho of r prime divided by r minus r prime. There is this additional vector. They look quite similar, except on this one. But one advantage we also have of using the potential is that, I mean, you remember how we calculated the electric field for a given charge distribution. We had to consider the x component, the y component, and the z component. All components we had to take into account. Because here there is a vector, we are summing over vectors. But now in the potential, there are no vectors. It's just a number. We are summing over the number, so we don't need to worry about the x, y, and z components separately. Once we calculate the potential, of course, we can evaluate all the components of the electric field by just taking the gradient of the potential. Yes. No, okay, so from the second line to the third line. Well, physics is nice. No. You see, what are the, I mean, in general, if you remember your mathematics courses, you will probably remember some discussions about whether you can exchange the order of the derivatives or exchange summation with integration, the order of the summations and integrations, etc. Now, the cases in which you cannot exchange them are what? Your function is not smooth, it has some, let's say, it doesn't have limits, it doesn't have derivatives, some derivatives, etc. Well, a function that doesn't have a derivative basically means it has a discontinuity. For us, it has a derivative because the discontinuity is a Dirac delta function, its derivative. So that's smooth enough for us. And furthermore, I mean, even a Dirac delta doesn't really exist. So all physical functions, all the physics that we know is smooth. Everything changes smoothly. Well, we will see one case where the textbook example, it will cause some problems. We will see an example. Other questions? Yes.
Potansiyel, bir dakika, elektrik alanı potansiyelin diverjansı gradyanı ya. Ama ikisinin arasında neredeyse hiç fark yok. Sadece bir sondaki şey var. Vektör şeyi. Yani niye öyle görünüyor?
Well, let's see. What is the gradient of 1 over r minus r prime? Do you remember? Did we discuss this? Now, this part that you say that the only difference, or I said that that's the only difference, is an important difference.
Peki hocam eksi işareti nereye gitti?
Hmm?
Eksi işareti nereye gitti?
It is right over here. This is where you have the minus sign.
Yani şu integralin başında yok.
Of course, because the minus sign is over here, not in V, not in E. It's in the relation between E and V. We have this minus sign or this minus sign.
Hocam, yukarılarda potansiyel anlatmaya başladığınız yerde sınırları değiştirdiniz. Biraz daha şöyle. O pardan oraya gitmiştik, sonra işte oradan A'ya gitmiştik. Burada bu you have the K constant, but it doesn't make any difference for the potential.
No, it does make a difference for the potential. It doesn't make any difference for potential differences, neither for the electric field. It changes the value. That's an important difference for the potential. But what we measure is the electric field. It doesn't make any difference for the electric field, neither for the potential differences.
Hocam, A'dan B'ye gitmekle B'den A'ya gitmenin hani elektrik alan için aynı şey olduğundan bahsettik ya.
Well, you see, the electric field doesn't go from A to B or B to A. At every point we have an electric field. Yeah. If we just, instead of from going O to B, you go from B to O, what you do is you just change the direction of DL. Nothing changes for E. It's the DL that changes. Yes?
Peki, demek istediğim şey şu, curl sıfırdan farklı olan herhangi bir vektör olan için bu vektör field için bu geçerli değil aslında, değil mi?
Now, for any vector field, the integral of V dot dl from the point A to the point B across path I, let's say. Any vector field, whether its curl is 0 or not, I don't really care. If the curl of V is 0, that just means that the integral from A to B doesn't depend on the path. This is always equal to minus from B to A across the same path. This is always true. Whether V is a vector field, has curl 0 or not. Because you see, once you fix a path, to evaluate this integral, you just divide that path into small segments, and dl is your displacement at every step. If you go from B to A in the opposite direction, instead of A to B, you are changing the direction of dl. So dl over here and dl over here have opposite directions. So to equate the two, we put this minus sign. Any other questions?
volume göreceğimizi söylediniz ama potential ile potential enerji arasında difference maybe.
Well, it's like the difference between semi and Fuyan. They have nothing in common. Well, they are related, just like you are related being in this classroom, but they have nothing common. They are not the same thing. Potential and the name is kind of confusing. Potential is not the potential energy. They are related. We will see the relation, but they are different things. And the unit of potential, unit of the electric field, Newton per Coulomb. Unit of the potential, well, it is Newton per Coulomb times meter, which we define as volt. So the electric field, we can also call it volt per meter. Okay, let's go for a break and see you after 10 minutes.